Okay, so hi everyone. Welcome. Today I would want to talk about this paper in our reading group. And it's related to my PhD topic, and it might be of interest to some of you. First, my name is Ahmad Nasser. I'm a PhD student. I've been part of Link since last April, and I'm doing a PhD as a collaboration between Nokia Labs and INRIA in Sofia Antipolis. And basically the paper Neo, yeah. And my supervisors from Nokia are Fabio Canise, and from INRIA is Giovanni Neglia and Xuan Chu. Basically, today's paper is a training algorithm for federated learning under heterogeneous targets using a technique called ordered dropout. So I will get into that in a minute. Basically, after an introduction, we will go through what's like model heterogeneity. I will introduce two techniques they used in this paper, which are ordered dropout and knowledge distillation. I assume most of you know the latter. And then I will introduce this framework they used and then some of the experiments they did. So to give a quick summary, basically in federated learning is a type of training method where you are doing distributed training of a neural network across different devices. So you have a neural network and you have a bunch of devices connected. The data each device has its own local data set. In these cases, we call, like, for the rest of the slides, I will probably refer to the device as a client. And basically, each device has its own local data set, and we want the whole point of federated learning to maintain data privacy, so the data stays on the device and the server never collects it. And basically, as a simple baseline of federated learning is federated averaging, and this is the straightforward implementation. We would have a neural network on the server. It would be we would initialize it on the server. We would send it to each client. Each client does like a gradient descent training of the weights. Then we have these different sets of trained weights, and then they are all sent back to the server. And the server does like a straightforward aggregation, element-wise aggregation of each parameter of the neural network. Of course, in these cases, we have a huge set of assumptions, basically. First, we neglect, for example, the differences in data that might occur on the devices. So you have like main type of heterogeneity in data that usually happens in every realistic scenario of federated learning. So what if the devices have different amounts of data, which is not the main issue, but like what if also the distribution of the data is different? So if we have
the question, so there is something I don't get, is that usually my knowledge about federated learning involves, say, Markov decision or something like that, and at the same time that this averaging, there is essentially the averaging, but I didn't see, perhaps it's what you call the AI model.
So basically,
could be MDP or something like that, or
no, it's not I mean, there are different algorithms for federated learning, but the straightforward baseline in federated averaging, it doesn't involve any Markov decision process. Okay. I would say it's basically we're doing like these parallel, like in optimization of the weights in parallel on different data sets, and we are, let's say, hoping or assuming that they would all converge to the same minimum, and then we do this averaging, and we would say, okay, our global neural network is trained.
Okay, so this the optimization, it would be like multi-layer or deep learning, yeah, for instance, and the weights would be the weights in the AI model, mm-hmm, and you have data sets which are like distributed or something like that, mm-hmm, and you do an averaging of the weights in the
yes, yes,
right. So it's linked in a sense, because I mean, so there is an optimization problem or something, which is not NLP, yeah, but the multi-layer or the deep learning thing with the weights.
So, for example, if all the clients have the same data set, let's just assume like this scenario: all clients have the exact same data set, and they do the exact number of iterations, and all the seeds, the random seeds, are the same. They would actually do the exact same mathematical operation. They would reach the same minimum. Then we average, would be also the same, and this would be like the global trained weights. Of course, this happens in iterations. So for example, we start with round 0.
So with the assumption that the model clients is the same, the global model, like they have the same.
Yeah, exactly. It's the same neural network, just different sets of trained versions. And basically, so of course, like this doesn't happen when we have heterogeneity in the data. So for example, if we are talking about like a data set like in supervised learning for image classification, like CFAR10, and which has like 10 classes. And then like you have red client here only has data for like 5 classes, and then the blue client has data for 2 classes. And then when they are doing this different optimization processes and we're averaging again, they cannot really converge to the same minimum or the exact same, they cannot resolve the exact same weights. So when we do the averaging, this becomes like more hard to find an actual global optimal weights. And basically, the other type of heterogeneity that we have, and we are also assuming, which is not realistic to assume in federated learning, is that the clients all have enough resources. So for example, they all have like enough computational power, so they would receive the weights, they would do the training nicely, and they would like send the weights back, and everything's happy, and they all arrive in time, and everything is working. And at the order, for example, they also have like enough communication capacity, so they can receive everything in time and send it back in time, which is also not realistic because, especially if you talk about a big neural network, not like a linear regression model or something.
So sorry, about the data, you were saying that if a single model doesn't see enough of a class, even if the other one will, then when you average, you won't get a good global score, global. Like,
basically, we would be averaging between two different different minimizers. And basically the more heterogeneity in the data, the more it would be like we're trying to find this compromise between these very different functions we're minimizing. So the worse we would expect the performance to be, the overall performance. And now basically in terms of resources, the same thing happens. So for example, if we're doing the same as we had said before, federated averaging, but some clients are weak, so they don't do the training in time, or they don't even have memory, for example, to have a big neural network, then basically the server would have to just drop these clients, like not use them. And then basically we lose, first we lose a lot of data that we could have trained on, and second, it would affect performance because we lost so many clients. And one of the solutions or the things that we can do to handle resource heterogeneity is model heterogeneity. So instead of having one big model we put on the server and we send it to all the exact same model to all clients, what if weaker clients, we can send like a smaller model, something smaller that they can handle, like they can download, upload, and train successfully with their resources. In that case, we would be fitting the resource constraints of each client. And at the same time, everyone would be participating, and we would get the trained versions like of the weights from everything. The only problem is that if we want to handle model heterogeneity, how can we would come up with like a bunch of questions or like small other challenges. First, like how do we create the small models? So if you have one big model and then you create a smaller model from nothing, okay, you train them separately. Okay, how do you combine them? If they are like completely different, they're not from the same even architecture. Okay, if you do them from the same architecture and they are trained on two different functions or objectives, how do you combine them again? Some neurons would be trained in this small client or weak client, and all neurons would be trained in another client. What is a good compromise that you can have? And third, like how much sacrifice do you accept in the performance? Because of course it wouldn't be the same efficiency and performance that we could have.
Question. Okay. So sorry,
no,
slow, but okay. So it would be good to have a concrete thing. So assume you have ReLU and weights to optimize and local data, something like that. So then all this would be of this type, but would work on different data or would have different structures. I mean, what are instances of the local AI models? And what are instances of a global AI model, global service coordination? Just, I mean, an instance.
I can show that in a minute.
Oh, okay, okay, thanks.
No worries. So this is where I get to like the point of this paper, or what does this paper do? But to answer your question first, I get into that. So for example, let's say this is a neural network, a deep neural network. We have these neurons and everything. A smaller model would be like just a model with a smaller number of neurons, basically. But the issue is that this works. Like if you just send a smaller model to a client, it would train it with the data it has. But then if you have these two different sets of trained neurons, how do you combine them? If you just do it arbitrarily, then it's basically we are ruining our own training. But this would be an instance. Now, in case of FjORD, FjORD is like a framework. In this paper, they introduced a framework that employs a technique called ordered dropout. And the idea is that this technique allows us to create smaller models from a bigger one, and in a way that would fit the computational requirements of each client connected. So basically, using this technique, we can create from big neural network like this here that can fit on powerful clients. We can create like smaller neural networks, subnetworks. So inside it, they are basically inside this neural network. We take a subset of neurons to create a smaller model that can be trained on smaller clients. Now, ordered dropout, it's like basically a form of dropout. So if we compare it to the random dropout, which is the technique used in deep learning, basically a random dropout, you would have like a dropout ratio, and we would basically in one iteration, a random dropout would drop most of the like a ratio of the neurons, and only use a subset of neurons to actually do the forward and backward propagation with a gradient descent. And basically, an ordered dropout would do the same in principle, but it's basically enforcing this natural order of importance on the neurons. So it would only pick the most important neurons first. So in ordered dropouts, let's say we have the same neural network of 3 layers. We are always enforcing, like in this case, the leftmost neurons are the most important, and it goes down, like it decreases in importance.
Sorry, Ahmad. Like this concept of random, I didn't get it right because I don't think you can literally drop at random without having disconnected pieces of the network, right? If I have like for each neuron, I say I drop a kip, you have a risk of having...
Yeah, but you're only training the neurons that are like, so in here, for example, we would only be updating the weights of the neurons that are involved in it.
But you are, but you are optimizing, okay, yeah, okay.
So you can still get like a prediction, and you get like, you can calculate loss, but when you're doing the backward propagation,
But you decide to optimize just a subset.
Exactly,
okay.
Exactly.
Now I get it.
Yes, it's a dropout, so it's per iteration. So in one epoch, let's say you have.
It may be a problem. It may be only in this figure, but do you also select, for instance, which output layer neurons you train? Because that's also your classes, right? So the final layer of a neural network is basically the classes.
Usually with the dropouts in general, like you're neglecting the final layer. The final layer is you don't
do the dropout on the final layer. Basically, you don't do the selection.
Yeah, exactly. The final layer is just to give you the output. So this has to be
okay,
we cannot play with that.
The representation are everything but the last layer.
Yeah. Let's say these are the hidden classes. Let's say these are the hidden layers in a neural network. So in ordered dropout, you have this natural order of importance. So the leftmost neurons, for example, here have higher importance. So they always have high priority to be selected when the dropout happens. So basically, naturally, when you do this dropout, like ordered dropout many times during training, the leftmost neurons, the most important ones, are trained the most because they're always selected. And now this, if we want to go into a bit of more details, basically this gives us two things, regardless of everything I wrote, but we would have like this structured pruning of federated learning, not something random. So you have this pruning mechanism that we did that would tell us like which is like the best submodel that we can have, which is like the most trained neurons, let's say the most important ones. And then basically also we would extract these nested subnetworks inside one model. So for example, let's say we have this neural network like similar to before. If we have like 3 possible values for the ordered dropout ratio, let's say 20%, 50%, 100%, you would have like the full model 100%, then the 50% model or subnetwork inside it, and then the 20% subnetwork inside that. I'm not sure it's like a great approximation, but like a matryoshka, you know, everything's said, right? Another cool visualization, usually, of course, when they implement it, is usually we have like a finite set of candidate values for P, the dropout ratio. So we're not just like creating this continuous ordered dropout. We have like candidate values for P. So we have like, in this case, 3 sub networks, including like the biggest network, the full model. And basically, if we are doing different iterations, this is how it would work. Like if it picks the 0.2, let's say, we get, these are the neurons being trained, and then 0.6, and then 1. Now, this is the first technique, as we had mentioned. And the second technique here they used is knowledge distillation. And basically, in this case, they are referring to it as self. Sorry?
There is a question.
Oh, sorry.
Yes. So to decide, you select this proportion P, and I understand that you create the subnetwork with this proportion, right? But but you start from a side here, because but you must have knowledge already that the most important neurons are on the left or the top, right? And so
it's just a design choice from the beginning, because basically we initialize the neurons like randomly using any random function, and then we say, okay, like priority is like left to right, or like in a weight matrix is like this vector, like from this vector to this vector. Like it's just a design choice.
It is based on centralized training first to detect how to shape up this pruning, right? So you have to, the function has to be decided already, and it's based on earlier centralized training to decide that the most relevant neurons or sets of are on the top here, right?
Yeah, so basically this is a bit separate, like this discussion is separate from federated or not, or classic. Basically this works, let's say if we have like a data set and one device training one neural network, we can do this. So far, it's just a technique. Yeah, but I will see in FjORD they extend it to like the federated scenario. They show us how they do it in the federated scenario.
Sorry.
Yeah, go ahead. No?
Really decided, or it's arbitrary? So you say, since all neurons are born the same, you say arbitrary, I will take the left ones as the most important, and so since you train them, they will become the most important. So it's
exactly.
Okay, but I am. It is strange for me to see that you also disable input features, right? Because it's strange. So, and this you do also arbitrarily.
We were talking. So basically, this is, let's say the visualizations are mainly the hidden layers.
Okay, yeah, sorry.
Ignore that. But no, I get, because I put X and Y, so it's a bit, I just meant by X and Y, like to know, like, okay, it's going this way, different propagation, and not this way. So the other technique they used is knowledge distillation, which is like a technique that when we have 2 models, a teacher and a student, the teacher is not being trained, we want to train the student, and the student tries to mimic what the teacher predicts. So the predictions of the teacher are labels for the student, let's say. Like this is in principle. In this case, they call it self-distillation, because basically we said, like in our scenario, we have a network and it has a bunch of subnetworks inside it. So what we're doing here, like they're saying, okay, we're taking the teacher, the full network or the biggest network we can have, and the students are the subnetworks inside it. So we predict with a big model, then we use it as a label to train the small model. And it goes again and again. And basically, it supports this nested structure. And this is like an example. So if you have like, this is like the neural network, then we have like the full model, like let's say the teacher, the biggest model. So we have the softmax of the biggest model. And then you have the softmax of the smaller model. And then you use, to train this set of weights, you use like first like the predictions versus the labels plus the predictions versus the predictions of the teacher. This can be seen in like this combination of loss, for example. Then here we're talking about like classification. You have a cross entropy loss. It's like a weighted sum of the predictions of the small model, SMP. Okay. And then these are the predictions of the big model, SMP max. And you have this weighted loss between them. So cross entropy of predictions of the small model versus the labels, which is from the dataset. And then plus the KL divergence of the predictions of the small model versus the big model. And KL divergence, basically, in a nutshell, it's like something to measure the difference between two probability distributions, how different they are. So if we have the exact softmax predictions, it would be 0. If the two models suddenly like predict the same thing exactly, let's say, for every class.
Sorry, question here, because sometimes I've always found in this form the parameter temperature, but I kind of don't understand the usage in general and also here. So what is the temperature doing?
Basically, it's basically it's related to like how the I'm not sure, honestly. I'm not confident enough to answer you.
Because so I always find the formulas like this where we know that the divergence is depending on the temperature, but I don't know what is the effect. So I heard that, but again, I'm not an expert, so I know that it has an impact on the kind of exploration degree that you can allow. Like if with high temperature you risk, you interpolate more, and so you have more chances of getting unseen data classified. But on the other hand, for instance, if you consider the natural language model as an example, low temperature means if I'm not sure, I don't predict. So it's this kind of relationship. High temperature, I predict even if I'm not sure, and low temperature, I only predict if I am sure. So in your classification example, it may be related to that, but I don't know. Again, it's
Leonardo?
Yes.
Maybe I have an explanation, but I'm not sure because I'm not an expert in this domain. To me, it recalls me simulated annealing. And in simulated annealing, when you try to optimize a function, the temperature indicates how much you can escape a local optimum. And so the lower the temperature, the more you are trapped in a local optimum, and the higher the temperature, the more you can escape a local optimum. And so when you are about to converge, you try to decrease the temperature, and while you are in the exploration phase, you try to have a high temperature. But I don't know if here this is the same kind of temperature they are talking about.
I think it matches a little bit my first naive impression.
Maybe.
Yeah,
maybe.
Because if you are in a local minimum, maybe high temperature, it means that you have higher chances of getting a point outside of that local minimum, because you jump higher. You try, yeah. Thanks.
There is a proposal in the chat for the explanation of the temperature.
One question. The softmax is the rule you use to pick the answer, right? The classification. How does it work? So you have the last layer with a vector of probabilities, I guess.
Yeah, so exactly. So basically, in a binary classification, we would have like a sigmoid function at the end of a neural network it's from 0 to 1, and what's in between as a probability if it's like 1 or 0 in the classification. When we have multiple classes, so let's say 10, it basically the softmax predictions are like a vector of 10 values that are representing the probability, like for one sample, the probability of each class.
And you just maximize.
Yeah, so the highest probable class would be the thing the model predicted. Using these two techniques, as we had mentioned, ordered dropout to create these subnetworks and knowledge distillation to add like another feature of like transferring knowledge between these subnetworks. FjORD basically came up with, like FjORD is basically a framework that they came up with, where basically you have like a global model for federated scenario. You have a global model F, and its weights are omega t, like at round t, and we have a set of dropout rates that we have. They correspond to models, so each rate is like one submodel or subnetwork, and you have like clients that are grouped to clusters or tiers based on like similarity in resources. And then in each round, T, we have like a subset of clients that are actually participating in this round. It's called ST. And then during the local training, each client receives like the maximum model, the biggest model it can hold. And it runs like iterations, local iterations on it using gradient descent methods. And this is something that we can see this framework. So as we had said, we have like global rounds for each round. We have a subset of clients participating. Now for each client, the server sends the weights of the submodel that it can hold, the maximum submodel it can hold. Each client has, as we said, like one PI max, which corresponds to like the biggest submodel it can have. And then after the client receives the weights, basically it does like local iterations. And in each iteration, it samples a value, PIK, like each client I samples PIK. And basically, this is a value that corresponds to one of the submodels it has. And then it trains that subnetwork or submodel based on, as we had said before, on ordered dropout. So to also show this a bit more, so for example, one client might have a PI max of 0.6. So in every iteration, it picks either 0.2 or 0.6 to train.
Okay.
Yeah. And of course, like if you are the most powerful client, you would have the full thing and you would train whatever you want. But that's how it works. And then after, of course, after each device like does the local iterations, it sends back the updated weights to the server. Then the server tries to aggregate everything together. And now the aggregation part is a bit tricky.
Sorry, why it picks at random and why it does not train the biggest it can?
Well, basically, okay, cool question. So basically, if the client, let's say each client trains the maximum model it can hold and it ignores the smaller ones.
Yeah.
If we do that, then the smaller models would only be trained by the weak clients. Like they would only be trained by the data of the weak clients.
Yeah.
But if the most powerful client sometimes trains the small model, then the small model is being trained by all data sets across all clients during across training, I mean, over iterations and rounds. So it would be beneficial.
Yeah.
But it would also, this is a very long discussion.
And sorry, another possibly very dumb question, but if I use the same data to train two submodels, then what I am doing, I'm like biasing the global one.
It's not useful then. No. Why should you train on the smaller one? Will you slow down if you have the same data, you know?
Yeah, so basically you are benefiting the small model for sure, but you're not really harming the bigger one in principle. But this is like an interesting scenario. We can talk about this in the end. So for the aggregation, so when we send back the weights, the aggregation happens, and because we have this heterogeneity, so we have different matrices, and they're all like different sizes. So we're talking inside one layer. So basically, it aggregates like as a weighted average. The weights of this average are based on the number of data samples on each client. So the client that has more data has more weights. And we are aggregating, like we're averaging every subset of parameters that are trained by corresponding clients. So if a client is too weak and we're aggregating the least important parameter or neuron, we're only doing the weighted average for the powerful clients because they are the only ones who actually train that parameter. So if we say like, hope that's not too confusing. So if you have in one layer, like one weight matrix, the smallest model like has this these parameters here, and then the second, like the bigger model is this, and the bigger one is this, until we reach the full model is all of this. So when we do the aggregation, we do first for this, and every client trained the smallest subset, and then we do the weighted average for this set, which is only trained by like 80% of the clients, and then this set trained by 60%, and then this set trained by 40% of clients, and then this set trained by 20%. This is what we mean when we say like this difference. Like, so we have this subset of parameters. Like we're talking about like slices. We sliced up the parameters and we aggregate for each set separately, and these sets are disjoint.
It looks, I mean, surprising because, I mean, if I get it correctly, you don't, for the data which are on the top left corner, which are, if I get it correctly, the most valuable.
This is the most valuable parameter or most trained.
You don't benefit from the global training, but you use the values that only those having a very short.
No. Basically, okay. So if you have one client that trained everything,
yeah,
then it participates in the aggregation for this subset.
Okay.
Yeah, but for example, you have clients that only train the small subset because they are weak. So when we calculate for this subset, they are not involved in the aggregation because it's zero. It's like they didn't participate in anything.
Okay, so we have to look again then at the aggregation function, because I mean, so what you say, which makes sense, that why ignoring the global thing to decide of those in the left.
Yeah, exactly.
Right. So okay, so this you have to say a few words on this equation now.
Yeah. It took me actually a while to actually know what that means.
Sorry.
To actually get this equation, I had to look at the code of the paper to read it to actually know what happened to get to what they did. So basically, I think I put.
Sorry, I have a small question.
Yeah.
Does it mean that you assume when you do the aggregation that the position of the neuron is mapped to the role of the neuron? Because otherwise you might aggregate neurons that don't play the same role in the both network, and so you will do weird things. You see what I mean?
Can you repeat? Sorry, I didn't exactly get it.
If you aggregate two layers of different shapes, especially, but even if they are of same shapes, the problem is the same. And if you map one by one each neuron, you assume that the neuron that you combine play the same role, which is not guaranteed in general because it's not sure. You see what I mean or not?
I'm sorry, I didn't understand.
Okay, so often in a neural network you can. So it depends on the use case, but sometimes you can interpret the role of a neuron. For example, if you are in a CNN and you are recognizing numbers, for example, you can know that this neuron recognize, I don't know, circles. This one fires when you recognize lines or something like this. And at some point, when you aggregate two different neural networks, do you have the guarantee that you will merge neurons that are both recognizing circles and two neurons that are both recognizing lines, for example?
Yeah. I understand now. I think I get your point when we are doing this aggregation and this heterogeneous aggregation, and basically this small, like weak clients would train this set of parameters for a task, or let's say a job, like to detect certain features. and then the powerful clients would train it to detect something else. Yes, we have basically this compromise of like, they have to detect features that are useful for the small model, but they are also useful for the bigger model. They have to find a compromise in between. And when this happens, and this is basically what deteriorates the performance. So basically here, with what we're doing in FjORD, we like managed to make every client participate. So because we're creating smaller models, but then if we, let's say, if we have too much heterogeneity and there are too many models and too many different levels of, or like tiers of clients, then the compromise, like this mixed function, or the compromise we're trying to teach the neuron is not an easy one. So it becomes something, it actually ruins the performance in that. And this is something I will talk about.
Okay, and when you run the dropout, you only drop neurons, or you can drop also just a connection between two neurons?
No, it's only neurons.
Neurons, okay, thank you.
And so I understood the question, but I didn't understand the answer. So actually, each neuron has an identifier, right? This is the third neuron of layer number 4.
Yes.
And so when you aggregate, you take all for that neuron, you take all the third neurons of layers number 4 in all the models.
Yes.
So for sure, the role of the neurons, etc., are respected because the identifier of the neurons are respected when you aggregate.
Yeah, but for example, if you are a weaker client, let's say this neuron you mentioned is included in every model. So let's say it's part of this subset, okay? And if you're a weaker client, you would only train this neuron for one loss function, like the loss function based on the prediction of this model, you know?
Yes.
And then if you are, let's say you're a powerful client and you have like all of these submodels, then you are training this neuron sometimes to predict well, like this weighted sum of losses for all these models. Yes. So this is a weighted sum of losses, and this is one of the losses.
Yeah.
These are two objectives, different objectives, or we're minimizing two different functions. And then you say, okay, I'm going to aggregate or do an average. So it's going to have find like a compromise in between. And the more heterogeneity you have, the more difficult the compromise would be. And now to give like the benefits of the framework, like, and this is something by design, you can save a lot of communication because you reduce the transfer costs. You have less parameters being transmitted to every client. So this definitely like saves computation and communication. You also have like this neuron importance, and you don't have to do neuron matching. So for example, in some other methods, if you randomly select neurons to create a smaller model, then you have to, when you want to aggregate, match them up again, and which was what, and you don't have to solve this problem anymore, because basically for the same dropout ratio, you always have the same neurons. And finally, we have this subnetwork knowledge transfer that is happening, and or like self-distillation, that they also added it as a feature, let's say. Now the evaluation that they had, basically they did some 3 different tasks, 1 for text and 2 for vision, to do image classification. And they used like this set of models. In all the experiments we discuss in this paper, or they discuss in this paper, we have this 5 submodels for any model that we have, just so you know. And basically, you can also see for these 5 submodels, like how much parameter savings you are making, let's say. And all of this is completely, like, of course, by design. And they picked 2 baselines to compare with, something called extended federated dropout, and then they add that to FjORD. So to give a quick highlight, extended federated dropout first. Federated dropout is simply like creating a small model by taking a random subset of neurons and training it on a client, and then match them back to do the aggregation. This is federated dropout. Extended federated dropout is when you have different tiers, so you have different dropout ratios, but also random selection of these neurons. And then when they did, so this is the baseline they compared with, and then they added the extended federated dropout to FjORD. So basically, they do this, which is very peculiar. I haven't seen any paper do that, but basically they add the extended federated dropout to FjORD. So when you have a subnetwork, when a model can only have like one subnetwork, they, instead of just sending that model, they assume, okay, the model might drop out some of its neurons, the subnetwork, and might take some neurons from the other bigger models, which breaks all the point of having like these restricted subnetworks and all. It's a weird baseline, but they chose to work with. And first, in the experiments here, we are doing, this is a classical deep learning setting. So this is, we don't have anything federated here. This is only like to evaluate dropouts. Single model here represents like, what if we have, sorry. So what if we have this subnetwork as a single model and we train it from the beginning, completely just train it and with disregarding everything else, like the smaller subnetworks or the bigger ones. And this is what they're comparing with. And you can see, for example, in the case of ResNet 18 and CFAR10, it's actually ordered dropout with some knowledge distillation. It's actually matching almost the performance, and this is accuracy, of course, top one accuracy, the performance of the single models. In the case of like Shakespeare, it's a bit less, I would say. This is just a proof of concept to show the point of having ordered dropout. And then for when they wanted to come, right? So when we're comparing with the baselines in the federated case, in these settings, you have, like, as we said, 5 models, and we have 100 clients. 100 clients evenly split between the 5 on the 5 tiers or 5 models. So you have FjORD with knowledge distillation, and then you have FjORD with the 2 baselines, let's say, and this is standard deviation for each of the cases. And you can see that FjORD is quite superior to the 2 baselines compared. And then when they wanted to, they did this like experiment where they said, okay, what if we compare FjORD with and without using knowledge distillation? So when we are doing, along with the training with dropouts in FjORD, when we do this self-distillation, that's would be like the case of FjORD with knowledge distillation, and this was the performance basically. And this is all top one accuracy, and here negative perplexity. And you can see like knowledge distillation is quite useful for the overall case. But for example, here, if we compare it, you can see that, for example, without knowledge distillation, the smallest model actually achieved higher accuracy. And the benefit actually came to the biggest model than the smallest one. And this is something we also saw in other experiments in general, like this idea of when you have these subnetworks inside with the most important neurons. For the same big model, it actually benefits the predictions of the big model, because when it predicts, it gives more weight or more importance to the neurons that are trained the most. So there is some benefit there, but I would still not expect to have like this difference in accuracy in terms of the
sorry,
when we compare the 2 cases.
Sorry, maybe the stupid question. Which were the tasks here? The prediction, classification.
So here, this is classification of CFAR10. This is also a classification of MNIST. And here it's prediction of the next word with Shakespeare dataset. And these are CNNs. Well, this is ResNet 18, so it's a standard model, but this is a CNN they came up with.
And do you have also information about the inference time of, especially for the RNN, because those are recurrent units, and when sequential data are need to go in many layers of recurrence, it takes time.
Yeah, I think well, this depends on the RNN they use, but as far as I remember, they didn't use any standard RNN, so it's just, I think it's just a simple short RNN they came up with similar to the CNN. But I can check. I don't have the inference time.
Yeah, it's okay. Because actually there is also another Another maybe more general problem with federated learning, and especially the model slice that you were doing, because for instance, if you use LSTM, and they have this kind of attention units, right? So you need to keep track of the previous context in order to make both inference, but I guess even for training you need this part. So if you happen to have some clients in your federated learning model that do not have the full span of the context that they require, maybe the performance in the AI sense will be lower, because they lose.
But I think in the LSTM, in this case, they will just use the let's say this mechanism only for the MLP part.
Okay, so not.
I think so. Yeah.
Okay.
I mean, I cannot say like that's what they did, but that's what I would do if I was doing it. And then here we have like some comparison in terms of scalability. So if we have, instead of 5 submodels, if we have like 10 submodels, like of these two cases, which doesn't seem to affect performance that significantly. And finally, we can see also here for the what if you have different device distributions. So here, like before we had like this even split of devices on the 5 tiers. So we have 5 submodels. Each submodel has 20 devices with that capacity. So here they said, okay, what if we have like half of the devices for the biggest for the biggest model, and then the rest are evenly split for the smaller ones. And this is the comparison that they have. Wow. Yeah. This is one of the same. So I mean, as the conclusions of this, they were able to, let's say, develop this framework that was designed for heterogeneous devices or clients, and implement like this technique, ordered dropout. They didn't develop the technique, by the way. I think it was, they cite 1 or 2 papers that did this for something else, but they are the ones who actually integrated it to federated learning. And like use ordered dropout to extract submodels from a larger model. And then they were able to outperform the competing methods in local and federated settings. And as a future work, they mentioned that they would maybe extend the FjORD to future generations or further development, and maybe also like include data heterogeneity. Because one thing I noticed about the experiments is that in every experiment in this paper, regardless of which model or whatever, it's an IID distribution of the data sets. So even if you have different number of data samples on each device, but still it's an almost even split of among the classes. So, and this is not realistic really. And then they talked a bit about like inference techniques, dynamic inference techniques for heterogeneity. Now, one thing I can cite from my work a little bit, I can mention, is that it's not always that pink. So, for example, I have a couple of minutes. So, for example, like we did take their repo and we did this quite standard experiment where we said, okay, we have FjORD. This is without knowledge distillation, standard ordered dropout. And in the same scenario they had in their experiments. This is ResNet 18, CFAR 10 for image classification. And we defined like an upper baseline, like here, this is when you don't have resource heterogeneity and every client just trains the big model and they don't care about the smaller things. And this is like the standard. And we could say like we just assign this to be like the best performance, the upper bound that we can hope for. And then this is the performance of FjORD, and then these are the baselines. So these baselines are like the trained sub-networks on their corresponding clients, but they are trained separately, so not like together. So we can see FjORD actually performs better than them. But then I took the smallest model, like the smallest sub-network, and I trained it on all clients because every client can fit that. It's the smallest thing. And if you train it with simple federated averaging, nothing special at all, you actually get this performance, this top 1 accuracy. Yeah, so this is something, okay, this doesn't apply all the time.
So you train data.
The same setting, the same type, number of clients, the same distribution of the data, the same everything. But instead of these clients having having bigger models and doing this ordered dropout and knowledge distillation and all of these things, they all just take the smallest model and they just train that. They don't do anything else. And this is what I got, which is quite peculiar. So for example, if let's say we had a different heterogeneity, so we had like the smallest model as 0.1 or 0.05, so it's super, super small. If we had that, maybe we didn't have this extreme case. So it really depends on the type of heterogeneity you have and what you're trying to do. But it calls to question a little bit, at least, is it always is this like an optimal way all the time or not really? Sorry, yeah, go on.
The first one is very dumb. No, stay on the on this, please. So the first one is very dumb. You have the blue line on top.
Yeah.
If I do everything centrally, so if I take...
not centrally, everything's
federated. Yeah, but this is the dumb question. If I do everything centrally, I go up, right?
Yeah, or something very similar to this, but it should be up. It should never be down.
Okay, but do you have a feeling of how better I can do? Like I'm close there, or I'm really losing something on doing this?
I mean, this is around 89. So this accuracy of the upper bounds. It would be around. I've done this experiment. I think it was around 91, 92, something like that.
Okay, thanks. So when you say that you train the smallest model everywhere, if I got it right, when the clients train the small model, they don't train the small model on all the data, because the ones that can do bigger models will use just one fraction of their data for the small one. So if I can do model 1, 2, 3, 1/3 of the time I will train the small one.
That's correct in one round. Okay, but we're having okay, if you do one round, so you have let's say one epoch, you're doing one epoch. So yes, not all the data would train every model the client has. But since we're doing rounds, so usually, for example, these experiments, we do 500 rounds. So in each round, the client gets the model or along with the submodels inside it, and they do this training. So at some point, you can conclude that, okay, this data was used for this submodel because of how many times it's being actually.
Okay. And then, do you know if anybody took the vanilla federated averaging and looked at what happens if you give a different distribution of the training data to the clients? Not this guy is in this paper, but that would be very interesting to see.
I think that's done. I cannot cite a paper off the top of my head, but I think that's probably done.
Okay.
It should be.
If you have a reference, I'm happy to have it.
Okay, I will.
If you come across one, please send it on.
Sure.
Thank you.
Thank you.
I have a sort of more math question. So, I mean, when you distribute, so you are running optimization problems in a distributed way. So I would like to understand the cases where it doesn't work. So is this linked to oscillation? I mean, because when you distribute the thing, assume the initial problem is well posed, there is a sort of, the optimal weights for the problem. And I know you distribute the thing. So when it goes wrong, what are the fundamental reasons? Is it linked to, a fight between this optimization, because you have distributed the optimization, and then things starts to oscillate, and you never zoom. So what is the?
This is a more general question.
Yeah.
So it's not resource heterogeneity. It's just in general, right?
Yes, about the distributed nature of the optimization with this way of cutting things into pieces.
I think it comes down. It comes down to having different functions minimized on different clients.
Yeah.
Because let's say if they are all minimizing the same function, even with different data, but it's very, very similar, then even if you average whatever you do, like however like the exact details are, it would still converge to the same thing, around the same thing. But for example, if you have a lot of data heterogeneity, so like you have one client that only learns to classify one class, or like to distinguish between two classes, and then you have another client distinguishing between two different classes. And then if the data set is hard, for example, so these classes are very different from the other classes, let's say one client tries to classify two classes of triangles, and then another client trying to classify two different types of circles. Like this task is not related to that task, or maybe one of them is like colored, some of these classes. And then when you want to simply average the weights, we're not talking about like knowledge distillation or something high abstract. It would basically, you would trying to find a compromise of two functions that are minimized so far in, like I said, the optimization space. Like it's two completely different functions. But if the functions were very, very similar, whether because of the data is the same or because of this exact setting that we have, type of data set we're using, it's an easy one, let's say, data set, even with heterogeneity, then you would have some success at least in doing this averaging, because the tasks are similar.
I see.
The features learned by the same neuron on two different clients is useful to both tasks.
I see.
But if it was like, if it's useful only to this task and not useful to this one, and then you average, then basically it's like learning like a very naive thing.
In that sense, I mean, something of this nature can be destructive compared to just doing the thing with one. I mean, if you have if you don't have this type of consistency, it may be worse than ignoring the input. That's the. And so, is there like a classification or something, an understanding of when it could be used and when it should not be used?
I don't think there's a standard for this, honestly, because I think, well, first thing, it's usually most papers that we're doing like standardized data sets and different type of like classification or like next word prediction or something like that. So I'm not sure there's one metric or standard that is like general to like multi-purpose to realize this. I don't think there exists.
That the distribution of the clients is very, very different.
It may destroy the. It may be worse than doing just one.
I think so, but probably it has been looked at somewhere.
It should be good to have principles, right? Because if you introduce something that may be worse than, I mean, a federation which is worse than without federation.
Yeah, I mean, this is also even like in resource heterogeneity. Like we did some experiments a bit like, okay, what if we ignore the biggest model? Let's not train it. And let's use these powerful clients to train more the smaller ones. We actually achieved like a performance that looks like this, something like this. So it's on average, it's higher accuracy for everything. So it's yeah, but the big is basically became like the most powerful clients. Instead of inference with the big model, they infer with the second biggest model. And when you do that, then it's you can actually achieve a higher average accuracy of everything. All the accuracy for all clients is for all models is higher, because they all benefited from having more clients training these smaller models. And at the same time, the clients can, for inference, they can have the smaller model. It's not the powerful client; they can have any model. So there's I would say like the more difficult the task across different clients, the more destructive like the federation might be.
Regarding the question of François about the bad things that could happen, I would recommend you to read the paper named NEAT, N-E-A-T, which deals about neuroevolution, and the idea of the paper is to maintain a population of heterogeneous neural network that you try to combine using a genetic algorithm. And so they explain that you have to be very careful in the way you maintain your population, so that when you do a crossover, you combine the appropriate neurons all together. Otherwise, bad things happen. And so this is referring to my first remark in the middle of the presentation, but it could probably also give insight to François to understand what bad could happen when you combine two neural networks, and in particular in this context, because here you have no idea of what you average.
Yeah, can you first just put the paper in the chat, please? Just or the acronym.
Yes. NEAT. I will try to find the link. Yeah, the links. Yeah, yes.
Great, thank you.
And I also have another question. It's also general, because in the algorithm, the optimization algorithm that you showed at the beginning, I think it's quite common for federated learning. You have a set of clients, and then you choose how to distribute the models or the data to clients. But what I am wondering is, during the training phase, is the number of clients something that can change, or you assume that it's always the same? Because let's assume that you are doing a training, you are in the middle of a training phase, so epoch number, I don't know, 3, 4, etc., and then your number of clients changes. Will you throw to the rubbish everything that you have done before, or can
no.
No.
No. Basically, even if the number of clients changes, or like there is like other benchmarks, for example, when the problem is focusing more on resource heterogeneity for communication, we assume sometimes that some clients just don't respond. So we send the weights, they don't send something back for some reason. Still in that case, the learned weights that we have, the aggregated, they're still valid for continuing the optimization. But basically, you would lose clients. So if you have some clients drop, you would just lose clients to train, so you lose data to use.
This is on the case that you are losing clients. What if you are adding clients, for instance? Because suppose that you have 5 clients, and so you've chosen 5 different ways of distributing things. But now suppose that your clients are 10 or 15.
Okay.
Then you need to redistribute the learning to all the different to all the new clients, in order to avoid to make repeated. I don't know, maybe.
You mean to incorporate like the new ones to have some balance, or? Yeah, I think what the learned function, like the global learned function, would change when you add some clients. It starts changing, shifting. Like usually in the federated averaging case, you have all clients are powerful. We don't care about heterogeneous resources, and we just pick like a random subset of clients that we can access in this round, and we do the training on that. So if the pool of clients changes, the global objective, or like the global function, is changing or shifting a bit, I would say, but this would depend on like if the data is different or something else.
Okay, thank you.
Can I have another question? So, so can you compare your figure with slide 19? So in my understanding, slide 19, that is their results. Yes. So here, what is OD, W, KD?
This is the centralized case. So this is the classic deep learning, not federated.
Okay.
Yeah. This is just here, like this part of the experiments is just to show that ordered dropout actually works as a method in comparison to the single model, if you just train single model. In my experiments, they are federated case.
Okay. So, so this means that it's so as I see when I saw this result, then I reinterpreted the loss function that you showed, because in the loss function you have an additional constraint, an additional term that is a sort of regularization term. Now I see this KN
here,
which avoids weights to be crazy. Here you are imposing that the first weights and then the 40% weights and then the 60 should be agreeing in something. And so this means that page number 19 is saying that this method is also useful to regularize a neural network, even if you forget about the distributed setting. Is this what they say? I mean, if you go to page 19. So they are saying that even if you forget about, even if you have just one PC, it's always better to use their method because you achieve better results with respect to training the useful way, the usual way. Maybe I was not clear.
No, I think like here it's like it's still the single model case, like the simple way to train is still achieving better than
Okay.
Yeah. I mean it's close. It's not
close,
yeah, it's not like high that immensely better, but this is just to show that in the classic case, as a technique ordered dropout, it would still match to some degree the single model case. But I mean the single model would expectedly like I mean, I think this would be like an upper bound. We cannot achieve. It would be really weird if with ordered dropout we can achieve a higher accuracy than.
I don't know. Maybe with few epochs it can be because it's a sort of regularization.
Yeah, but also like when you have these different. I mean, this is my point of view. When you have these different submodels and they're all training same weights for different predictions or different objective functions, the more consistency you have in the training, like let's say the same model is being trained for the same parameter being trained for the same function to minimize the same function, the more consistency you have, the better the final outcome would be. Because once you have this inconsistency, so you have different functions and the same parameters trying to learn something in between, you can never really. It should not like it would be really weird if you find like a better minimum, because like the case when you have one function, one loss function, and we're minimizing it all the time for this by changing the parameter, basically you would always it would directly go to the minimizer of that function. But then when you have like different functions, they're trying to find a nice sweet spot in between to.
Well, if you just look at the training loss, yes. But when you then look at the test loss, maybe it's good to disturb a bit the training loss to better generalize. I would be curious with few epochs how it goes. The last thing, so there is a non-linear relation between the weights and the loss function, right? And so I'm astonished that in federated learning, everybody just make a simple average of weights. I mean, are there people trying to find better ways of aggregating stuff, considering these non-linear relations between the weights and the loss function?
I think, well, there's the other ways to aggregate based on like when they take into account heterogeneity in data or in resources. If we ignore that part, both heterogeneities, I'm not aware of like a better way to aggregate. If we ignore both these cases, I mean, this might be true. I mean, this is a very basic like this. Federated averaging is like the first paper that said, okay, they didn't even call it like federated at the time. I think they called it like communication efficient, computation efficient case of like distributed optimization of a neural network, something like that. And then someone else came after and they said, okay, this is federated learning. So this is like the naive baseline to compare with. But yeah, I assume there might be like something else or more advanced after. The first paper was, I think, 2017 or 18, federated averaging.
You have a question on the brief?
So how can I see the chat?
It's in your laptop. I mean, you just you double click because it's in full screen.
If the model weights by dropping out everything from research devices, wouldn't that work heterogeneity in model rather than alleviating? If the model is by dropping out everything.
Thank you both. I mean, yes, there is a heterogeneity there. So, but this would still be. I mean, the main argument is that it would still be better than just dropping the full client and not using the weak clients. It's still like it's worse than if you had like both powerful clients and they are both training the same model and you don't have heterogeneity in the models, but it's still better than just dropping the clients and just using the powerful ones. So it's like some compromise you're trying to find to like the in between. But for example, if you have like all powerful clients, it would not make sense to even use ordered dropout or to train the subnetworks because you don't need that. And yes, in that case, the performance would be worse. I hope I answered the question.
So thank you a lot, Ahmad, for